today in light of the ongoing situations. But we anticipate to have our CT next week on Monday. I know we are going to lose 2 hours, and so it's important that at least we try as much as possible to catch up with the material that we cover. So what I'm simply going to do today is give you one last example. That I sort of explain that example to you guys. After you've done your CAT, we'll continue with the class as usual. So today, I'm simply going to introduce something that is similar to what you have in your notes, but it is not exactly the same. Please read your notes and look at all the examples provided in your notes. There is an example that looks like this, but it's not exactly the same as this because there's just a minor adjustments made which contribute to, in fact, significantly contributes to a change in how the system is analyzed. Now, this I've picked from one of the past papers. And the question here is that we have been given a translational mechanical system, meaning it's a mechanical system, but it translates one physical property to another. This system, like I've said, is quite similar to what has been presented in your notes, except if you check carefully, you will notice that the example that is in your notes has got only one damper, and that is the one that is damping the movement of mass 1. There is no damper between mass 1 and mass 2. But here we have introduced another damper between the first and the second mass, in addition to the spring constant. Now, typically, because of how we get the system equation, we know that the most basic physical variable here should be the displacement. Because if you look at f of t, if I decided to pull f of t, then I'm going to extend the spring k, and so we're going to have a spring constant k that is involved. But again, we are going to damp the vibrations between mass 1 and mass 2, and also damp the vibrations between mass 1 and the fixed position. So we are also assuming that this system is frictionless, because if it were, then we would also need to include coefficients of friction, which we don't want to complicate the system by including that. So we are assuming that our system is frictionless. So now, how do we go about this question? Like I said, the first step in finding the state representation of the system is to find the state variables. But those state variables clearly you could actually tell, because I told you for a lot of mechanical systems, they are easily identified as position, velocity, and acceleration, depending on the order of the system that you're dealing with, or the order of the differential equation that describes your system. So in my case here, the one you have in your books, I'll leave it to you to compare with the solution that we are doing here for the one that we have in our case here. And then you'll be able to see some of the differences that are involved, okay? Now, typically, I told you that if you're writing the system equation, or the equation that best describes this mechanical system, in this case, a translational mechanical system, we know that there's acceleration involved, we know that there's velocity involved, and we know that there's displacement involved. Key 3 things, even from the previous example we did. The acceleration affects all the masses. That is, acceleration will affect mass. Remember, I told you of that formula, F equals to ma. So the force on a mass is also dependent on the acceleration. The velocity would be acting on the dampers, and the position would be acting on the spring. The displacement, that is, would be acting on the spring. So the spring constant K will be brought into play. So like we did in the previous class, we could say that if we were to fully describe this system, that means we are trying to find the function f of t. F of t. How would we describe it? That's what I'm trying to see if we can come up with an equation that describes the entire thing. All right. So I challenge you to also try as much as possible on your own to write the equations for this system. Let's see. For mass 1, we have the mass 1. Somebody now, this is the time when somebody joins and then takes time to. So because I don't want to use the dots to denote differentiation and double differentiation, let me just write the differentiation in the longest way. So let me say d squared x1 over dt squared. So that's the acceleration. Because now you can see that mass 1 is displaced, the displacement for mass 1 is x1, and the displacement for mass 2 is x2. Okay? The resultant displacement is for mass 1 is x1, and for mass 2 is x2. So if I add this to, now I have two dampers. There's D1 and D2, and those dampers affect because you can see that damper 1 and damper 2, that is D1 and D2, are both connected to mass 1, meaning both of them affect the velocity at which M1 moves. So we are going to have D1 plus D2, okay, dx1 dt, plus the K is also connected to mass 1. So notice I'm trying to deal with mass 1 first and look at all the forces that are involved in mass 1. All the forces that are involved in mass 1. Of course, the mass 1 is also connected to the spring constant, so that affects the displacement. So I'll write K x1. Now, you can see that we have, again, damper 2 affecting, because we have to consider, in this case, unlike the one you have in your books, you have to consider all the forces that are involved. So we could say that we have to subtract, because I want to equate it to 0, so I'll have to subtract damper 2 dx2 dt, and then also subtract, because remember, the K and D2, that is the spring constant, and the damper D2 affect, it's joined both to M1 and M2. So I'm trying to subtract the forces due to the velocity, in this case, for D2, and the position due to the spring constant K related to mass 2, okay? From my first equation. That's why I'm subtracting those two. K x2 should be equal to 0. So this is the equation 1. So basically, I'm trying to eliminate all the forces that are due to mass 2, because I want everything for mass 1. But because the spring constant K and the damper D2 are shared between mass 1 and mass 2, I must subtract those forces, okay? Now, let's look at the next question, because we have to write two questions here. So again, now let me do something for mass 2. So for mass 2, I'll have first, clearly I can see here, I can indicate that I have to remove kx1, then I have to add m2 now, d squared x2 now, dt squared plus yes, I also have to have okay, so I've written that. So for the damper, I'll have d2, dx2, dt minus, because I haven't subtracted the damper due to, so minus d2 dx1 dt. I forgot to subtract that initially, but it's still fine. So plus the one due to, so that should be kx2, I think. Yes, should be kx2 should be equal to, the force on the other side is now f of t. Okay, so clearly, I'll be very, let me explain this. The first minus kx1, again, now I'm looking at all the forces that are acting on mass 2, but I have to remove those that are due to mass 1. That is why I'm subtracting the position, because like I've told you, the K and the D2 are shared between mass 1 and mass 2. So if I'm looking at the forces acting on mass 2, I am removing the forces due to the position and the velocity of M1. So that's why I have minus KX1, but I also have minus D2 dx1 dt, just like I did in the first equation. Then now I look at the force due to the acceleration here, which is m2 the x squared, the t squared, plus, of course, the force now due to the velocity, and also due to the position or the displacement of the second mass, m2. So clearly, that should be easy, but you can actually, when you look at the solved example that you have in the notes, you need to sort of compare the two and see the difference and see the significance of just introducing a damper in between mass 1 and mass 2, because it changes a lot of the dynamics. Now, this is where, after you've done, because this is just the system equation, but you have to now go back to finding your state variables. But you have to be smart about it, because remember, the idea was we have to come up with the state variables which are in the form of, and these are all vectors and matrices. Let me write it in a different format so that we don't, our idea was to get x should be equal to ax plus bu, and y, which is now that is state equation, and the output equation should be cx plus du. So this is our intention. So we have to manipulate our system equations to fit into the state equation and the output equation. One way to do that is to now, like we said, is to define our state variables. So what are our state variables? Okay, what are the state variables? We need to decide, what do we pick as our state variables? I told you that for most mechanical systems, it's easy to pick them because it's those systems that have their derivatives. If you have a physical quantity that has got its derivative, then those become can easily be picked as state variables. So if you look at our system here, you have x1 already is having a double derivative there. X1 is having its derivative here for velocity, and x1 is position in itself. So clearly, you can say your x1 should be a state variable. X2 for the second equation, you can also see, because it also has its derivatives, you can pick it as a state variable. But now, x1 and x2 are displacements, they're positions, that's fine. So how many state variables do we need we had said you need the minimum number of state variables that completely defines the system. A minimum number of state variables that completely defines the system. Now, let me take you back. I want to make this look easy. Let's say, let this double derivative, so that it's easy to deal with, dt squared for x1 be the same as, because we know it's a velocity. So it's like dv1 dt. Because I'm just saying, we know that the double derivative of displacement is the same as just the derivative of the velocity. That's for x1. And then the double derivative of x2 should just be the same as the derivative of the velocity v2, dv2 dt. So this is just an assignment I'm giving for velocity. So from here, you can see that velocity, or v1, has a derivative, and v2 also has a derivative, because we have dv1 dt and dv2 dt, where dv1 dt simply is referring to the acceleration for mass 1, and dv2 dt is also referring to the acceleration for mass 2. So because they have derivatives, v1 and v2 can also be state variables, because they have their derivatives. Okay? Now, this is equation 1 and equation 2. We can say that dx1 dt, let me just write it down here, dx1 dt, from what I did in the double derivative here, is just v1. So let me write it properly. I have a meeting to attend. It's v1, and dx2 dt is v2. Basically, I'm trying to say that if you get the derivative of the first displacement x1, that's the first velocity. You get the derivative of the second displacement, that's the second velocity. That's why the double derivative for the first displacement is just the derivative of the velocity, and so on. So that's just straightforward. Now, let's continue. Let me call this equation 3. I just want to make sure that I'm able to explain all these things. Let me call this equation 3a. I'll call this equation 3a. Now, I'll even come back just before I indicate this. I'm going to write it again. I want to write something here. From this equation that I've indicated, we can say that the acceleration d v1 dt, we have just said, is equal to d squared s. Like was what I'm actually writing back here again. But it's like I'm trying to find, remember, I want to replace the acceleration and write it in form of the other state variables. So from here we can see that if I make this the subject of the formula in the first equation, I'm making this the subject of the formula in the first equation. So it means I have to take all these other terms on the other side, and I divide everything by m1. And I'll do that also for the second one, where I'll take everything, I'll make this the subject of the formula, take everything on the right-hand side, divide everything by M2. That's exactly what I'm trying to do. And we did it also in the previous examples. So dx1 dt would be minus, I'm taking all this to the other side, so it's minus d1 plus d2 over m1 v1 minus just continue, please, just a minute. Sorry, ladies and gentlemen, I think I'm having technical issues here because I have been called out of this class to attend a very important board meeting. But please, let me just complete this in 1 minute because the board meeting, I think, begins right now. So I will just complete this for you here. What I'm saying is we just need to use 3A, 3B, 4A, and 4B to write the state equations and of course the output equation. So if you use 3A, 3B, 4A, and 4B, you should have in vector matrix form, you should have x1. I shouldn't be here now. Let me just write them quickly. And V2. Because you can see this is the x1, yeah, and this is x2, that form, and this is, of course, you have v1. This one is v1, and this is v2 derivative, of course. So I'm writing those in vector matrix form. So please go and check. If I am wrong, you will let me know that you arrive at this solution. So this is minus k over m1 minus d1 plus d2, I think in brackets, over m1. I think I have to change the way I indicate this. I'll have to write them in a my apologies. This is k over m2. I think I have to end this here. 1. This is minus d1 plus d2 over m1. This is 0. And this is d2 over m2. This is 0. This is minus. Okay. And here we have k over m1. Then we have 0. Then we have minus k over m2. Then you have 0. d2 over m1. This is 1. And this is minus d2 over m2. And so the state variables are x1, v1, x2, and v2. Okay, that plus, of course, everything here is 0 except the last one, 1 over m2, like this, f of t. Okay, so I've just written them in the usual form where we say these are the state equation. So you have your vector x equals to ax plus bu. So what I have not indicated here, which I'm going to leave as the assignment, is simple now, is just to write the output equation. Write the output equation. It should be a very simple thing to do, because you're going to have to put it in form of. So you have to figure out what is the output here. Okay, and the output should be clearly f of t. So the output y should be some vector here. Then you have the state variable, which is x1 v1, x2 v2. So please complete this. It's a very simple exercise that you can do on yourself. Remember, y is f of t. Okay, so please complete that, and then we will continue in the next class, because I am actually urgently required to attend the board meeting urgently. So please, my apologies, we'll stop here, and then we'll continue from here, where we'll now see how we can convert transfer functions to we can convert transfer functions and represent them as state space and also convert state space representation into transfer function. And we'll see why we have to do that in the next class after the CAT. So, ladies and gentlemen, I beg to leave. Thank you very much and see you next week. Bye-bye.